We have been learning about transition metal chemistry, and we talked about this interesting reaction of cuprates called cuprate coupling. And the idea here is that we're going to make this bond between an aryl carbon and an sp3 carbon. And we said the mechanism was not SN2. We've learned that transition metals do interesting things because they have a lot of electrons and yet also have a lot of empty orbitals. So we learned to look at this cuprate complex, recognizing that with a negative charge and two X-type ligands, the copper is in the +1 oxidation state, or copper 1. Based on what we saw last time with our standard sort of periodic table, which I don't have memorized, so I'm just going to copy what we drew here, right? And you'll have a complete periodic table when you take the exam, so don't panic. Let's see. I just sort of lost the screen I was at, so that's fun. Went up to the top. There we go. So there's our mini periodic table. Copper normally comes with 11 valence electrons. In its +1 state, it should have 10 valence electrons. So copper is a D10 metal. And if you count those 10 electrons plus the 2 that are in the metal ligand bonds, this is a 14 electron complex. Now remember that for transition metals, the magic number is 18. That's the new octet rule, the deca-octet rule for transition metals. They have enough orbitals to accommodate 18 electrons instead of 8. So when you see this number 14 and that it's not 18, you can see that there's space for more things to bind to the metal. That's important because that's what's going to happen in the first step. So as I said, in the first step, we take a pair of electrons, one of these 10 electrons from the d orbitals on the metal, and we form a new carbon-metal bond. And at the same time, we take the electrons from the carbon-bromide bond and we form a new metal-bromine bond. It's actually impossible to tell whether the arrows go this way or whether they go like this, and instead the 2 electrons from the metal attack, come on, there we go, the bromo first, and then the carbon goes like this. You can't actually tell, and that's okay. Either of them is fine. What we know is that afterwards, we have this new complex where copper is now bound to 4 things. And we know that we started that one of these 2 new things, ligands bound to copper, one of the bonds came from copper and the other came from the carbon-bromine bond. We don't know which is which, we can't tell. But if you look at this new complex, the overall charge is still negatively charged. The complex now has 1, 2, 3, 4 X ligands, so the charge on the metal must have increased to +3. It used to be +1, now it's +3. What happened? Where did those electrons go? It was these electrons. They came from copper and they made a new copper ligand bond. And as soon as that happened, we counted those electrons as belonging to the ligand. Okay? So if you want to, label things and sort of pretend, let's say these 2 electrons are the ones that attack the carbon, then we would say that the electrons from the carbon metal bond came from the metal, and the electrons from the carbon bromine bond, or the copper bromine bond, came from the carbon bromine bond. You can't tell really which one is blue and which one is red, but for keeping track of things, that's our purpose, right? So we call this reaction an oxidative addition reaction. It's addition because we added both this carbon and this bromo to the metal. It's oxidative because the oxidation state on copper increased from +1 to +3. Okay, questions about that? Okay. All right. So we can count the number of d electrons that are left on copper. Again, we can do this by coming up with copper's oxidation state, then comparing it to the number of valence electrons that copper normally has, which is 11. So there are now 8 d electrons. This is also how you can tell it's an oxidative addition reaction. Used to be a D10 metal, now it's a D8 metal. There are 8 electrons, 2, 4, 6, 8 in metal ligand bonds. So now there's a total of 16 electrons. We're still below the deca-octet or 18 electron limit. Okay? So this is a new mechanism. You haven't seen it before, oxidative addition. All right, and again, don't get too focused on which electrons are going where, because I've tried to illustrate at least a couple of times that you can't tell which electrons end up in which bond. As near as we can tell, the transition state looks something like this. Copper is here, its other ligands are here, and then here is the benzene ring. Oops, that's not a 6-membered ring. Here is the bromo group. Here is the carbon-bromine bond that's breaking. Here is the carbon-copper bond that's being made, and here is the copper-bromine bond that's being made. So 3 atoms in the same transition state. Overall complex has a -1 charge. So that's the oxidative addition step. Then the next thing that happens in the coupling reaction is we're going to do a reverse oxidative addition step. So to illustrate this, I'm going to copy the complex again so that we can draw it a little more cleanly. I'm going to erase the extraneous details. What's going to happen next in this reductive elimination step is that we're going to take 2 of the electrons, and at this point I'm going to drop the blue and the red colors and use them for different purposes. We're going to take 2 of the electrons in the red carbon-copper bond, and we're going to form a new carbon-carbon bond with the aryl ring. At the same time, we're going to break the copper-carbon bond. Now, I've showed the arrows that way. It would be totally fine to show the arrows this way. In fact, you can't tell the difference between those 2 options. So however you like to show it, the transition state would look something like this: a dotted line for the carbon alkyl copper bond, a dotted line for the carbon benzene bond, and then a dotted line for the new sigma bond that's being formed. Overall complex would still be negatively charged. At the end of this reaction, you've got your new carbon aryl bond that we just talked about, the one we've been trying to make, and the one we said that the mechanism was not, in fact, SN2. And then over here, you have copper now bonded to 2 things, an alkyl group and a bromide, and its overall charge is still negative. Let's analyze this complex real quickly. What is the oxidation state on the metal? Copper normally has 18 valence electrons. It has 2 X-type ligands. So overall charge is negative, 2 X-type ligands. What does the charge have to be on copper? Copper 1, a +1 oxidation state. Okay, number of d electrons. Used to have 10 valence electrons, but it's in the +1 oxidation state, so 10. You know, I can pretty well guarantee, my friends, that if we're spending time on this close to the exam, that you will have questions about this on a final exam. So you should work on this. Did I say too much? Okay. Too little, actually. You'd like a little bit more. All right. Overall electron count. How many? 10 from the d electrons. How many from metal ligand bonds? 4, so overall electron count 14. Over here, remember, this was D8 and copper 3, or copper in the 3+ oxidation state. So we're going to call this reaction a reductive elimination. In a reductive elimination reaction, electrons that used to be in a copper or a metal ligand bond go back onto the metal. Okay? So the blue electrons are now on the metal. We don't typically draw lone pairs on the metal. Instead, we do this math here to keep track of things. So oxidative addition, reductive elimination allows us to make new carbon-carbon bonds. And this is a pattern that's going to repeat in different reactions that we do. Questions? Yes?
Does the bracket cover just the CuBr?
The bracket covers the whole complex. I just don't want to draw the whole bracket. So there you go. And now that it's blue, somebody's going to ask, does the blue mean anything? No, it does not.
Does it not cover the phenol attached to the...
No, this is now neutral. And when we draw organic compounds, we're going to draw them the same way we've always drawn them. If there's any charge on the organic compound, we'll show it. For the reactions we're talking about, there generally isn't. Yeah. Others? Yes?
Yeah, on the transition state, did you say that electrons can attack either way? I didn't see that.
They could, yeah. So I've drawn the arrows where the red arrow goes from this carbon-copper bond to the carbon, and this arrow goes this way. You could draw them the other way. And in fact, most chemists will not draw arrows this way for this kind of reaction because you can't tell. Yep. All right, others? All right, so that's just illustrating what transition metals can do. What we're going to do now is dive into two, and we won't actually do too much with cuprate coupling reactions. It's just an example of a reagent you've seen before with chemistry that's more complicated than you were used to. It's a good way to introduce oxidative addition and reductive elimination. Now we're going to show you a couple of new reactions that make similar types of bonds, and we'll eventually get back to the molecule that I said we were trying to synthesize in the first place. So the reaction we're going to talk about now is named after a Japanese scientist, Professor Suzuki, and this along with another reaction we'll talk about today or next time is a Nobel Prize winning reaction. Like the cuprate coupling reaction, one of the starting materials is what we're going to call an aryl halide. When people talk about reactions like this, they'll often talk about substrate scope. That refers to the kinds of molecules that undergo this reaction. One partner on the Suzuki reaction is this aryl halide, which means an aromatic ring attached to a halide. The other substrate, or the other molecule that is acted on by this reaction, is either, in the example I'm going to give, it's a vinyl group, meaning an alkene with a functional group on it. But it could also be an aryl group, an aryl or a vinyl, and then the functional group that's on the aryl or vinyl carbon is going to be called a boronic acid, but it could also be a boronic ester. So I need to give you some examples of this. Let me just give you one. Boronic refers to boron, probably clear. What I've drawn here is a vinyl, that's the vinyl group, and then this group here, an R group attached to a boron, where the boron's also attached to two other OH groups, is called a boronic acid. That's a new functional group. You've never seen it before today. It looks kind of like a carboxylic acid, only there's no carbon and there's no carbonyl. Those OHs are slightly acidic, which is why it's called a boronic acid. You can sort of mix and match functional groups. Let me show you an example of a boronic ester. So an aryl boronic ester would look something like this. There's an aryl group, And then a boronic ester, a carbonyl, a carboxylic acid ester, has OR groups in place of the OH group. That's the same thing for a boronic ester. So if we replace the OH groups on boron with some alcohol groups, that becomes an aryl boronic ester. Okay, so just a little bit, I can't imagine that coming up. I'm just trying to describe the various substrates that work in the Suzuki reaction, and as I talk about these reactions in class, I may use these terms. All right. Yes. Sorry, where are you at?
Would it also work with like an OH and an R group?
Could you have one that's an OH and one's an OR? I think probably, but I don't think anybody does that just because there's no purpose in having that kind of difference. Yeah, that's a good question. Yes? Does it have to be an alkene? Either an alkene or a benzene ring, yes. Okay, so the Suzuki reaction is an example of a coupling reaction. And coupling reactions are kind of what we might call Lego reactions. We're going to connect this carbon to this carbon, and we'll do that selectively. There's a catalyst, but let me just draw the product for you, and I'll illustrate the new bond that we make. Well, there's the new bond that we make. Here is the aryl carbon from the original molecule, and here is the vinyl carbon. And notice that in the Suzuki reaction, even though the boron is gone, the stereochemistry in the starting material is the same as the stereochemistry in the product. That is, if your alkene has the boron trans to whatever group's over here, that trans relationship remains in the product. So you have some pretty nice stereochemical control. Does that make sense? Okay, so the catalyst is palladium, and a common catalyst is palladium tetrakiss triphenylphosphine. Tetrakiss is it's not 4 kisses. It means 4 times in like Greek or something like that. So triphenylphosphine. Okay, and you also need a base to help out with the reaction. All right, so that's the catalyst that does the Suzuki reaction. And again, notice the connection. Memorizing that, how this reaction works, is actually pretty easy because there are literally no other options. You put the aryl halide and the boronic acid or ester together, you make a new carbon-carbon sigma bond between the aryl carbon on the aryl halide and the vinyl or aryl carbon on the boronic ester, and the stereochemistry stays the same. There's not that many options. It's literally like clicking 2 Lego pieces together, right? So being able to predict products in this kind of reaction is actually pretty easy if you memorize the reagents and the substrate scope. We want to go a little bit, by that I mean the kinds of molecules that do this reaction. And then you just connect the dots. We want to go a little bit beyond that, a little bit deeper than that in analyzing how this reaction works. So I'm going to show you what is known. And this reaction is done so many times in the pharmaceutical industry. As I said, anybody that wants to go make molecules for big pharma and do research has to be able to do this reaction. The good part is it's a pretty easy reaction to do, which is one of the reasons why it's a Nobel Prize winning reaction. So let's show you how this works. We're going to start by looking at this complex between palladium and the 4 triphenylphosphines. Now you've learned from last time that triphenylphosphine is a what type ligand? L type. It leaves neutral, okay? The overall charge on tetrakiss triphenylphosphine palladium is 0. You can tell that because I haven't written anything, but I'm going to just write that here and tell you that it's neutral. So with that, and with our periodic table, which we'll now copy and move to help ourselves out, we can have an idea of what's going on with this metal. All right, all of the ligands are L-type. So tell me, what is the oxidation state on the metal? 0, has to be. If all the ligands are neutral and the complex is neutral, you can have no other conclusion than that this is palladium 0. That's actually a very common oxidation state for palladium. How many d electrons does this complex have based on its oxidation state and the number of valence electrons? 10, because 10 minus 0 is 10. Say it with confidence, it's true. Okay. So what about total electrons? Total number of electrons in this complex around the metal? 18. Okay, so that's a clue as to what has to happen in the first step. Is there any room around that metal for anything else? No, it's what we will call coordinatively saturated. That means it's got a full octet. Well, a full decaoctet, full 18 electrons. So it's thought that the first thing that has to happen in this reaction is that we have to lose 2 ligands. So the tetra-coordinated palladium species is going to lose 2 phosphine ligands. This will happen in sort of SN1 fashion. The ligand takes its electrons and leaves. That's called ligand dissociation, and it's generally rapid, and it's generally not that expensive in terms of energy. So it happens quickly and without a lot of trouble. So I'm going to just draw the 2 triphenylphosphine ligands that are left. Now, there is a whole field out there about transition metal complex geometry, and you have to know something about the number of ligands that are attached. You have to know something about the number of d electrons that are there. I frankly don't understand it because I never studied it. I majored in biochemistry, not inorganic chemistry. So there's stuff to learn here. We're not going to be very specific at all about the geometry of the complex. If you want to know more, you should take chemistry 514, maybe 518, maybe 552, maybe 569. There's tons to learn. With my colleagues, Dr. S., Dr. Michaelis, Dr. Stowers, tons to learn. Some of you are shaking your heads wishing I would stop talking about it, so that's fine. Now, notice that the oxidation state of this complex, the complex is still neutral. It's still palladium 0, but now because we've lost 2 ligands, this is now a 14 electron complex. That means there is room for other stuff to bind. Okay? So enter in the aryl halide. For us, in our Suzuki reaction, that was just phenyl bromide. So I'm going to abbreviate the benzene ring like this. And we're going to do what's called an oxidative addition step. We're going to do the same thing we did in a cuprate, in the cuprate oxidative addition step. That is, we're going to take a lone pair of electrons, one of the 10 d electrons from this complex, and we'll make a new metal carbon or metal bromide bond. And then we'll take the 2 electrons from the carbon bromide bond and we'll make a new metal ligand bond. I'm not going to bother pushing arrows because you've seen this before. I'm simply going to draw the complex that forms at this point. So you've got, I don't like those arrows. I wanted them to go a little bit further, whatever. All right, so in the new complex, you have palladium, again, with 2 triphenylphosphine ligands. Then you have a new phenyl, let's put the bromo here and the phenyl group there. Again, the complex is neutral. Let's analyze it real briefly. How many L-type ligands do I have? 2. How many X-type ligands do I have? Okay. I see what's going on there with the X's, so we'll just erase them. Okay. The overall charge on the complex is neutral, therefore palladium's oxidation state is, it's not 0 anymore. If it were 0, the overall charge on the complex would have to be -2 because of those two X-type ligands, right? So to get to the overall charge of 0, your palladium now has to be +2. It went up to an oxidation state of 2, it lost 2 electrons. Where did those 2 electrons go? It's in one of these new metal ligand bonds. You can pretend it's in one or the other, you can't tell which. 2 of those electrons came from the metal, 2 came from the carbon-bromine bond. Got it? Okay, so that's the oxidative addition step. Now, let's examine, let's see, we've got now, it's a D8 metal because we lost 2. It went up in oxidation state. And overall, how many electrons do we have? 16 total electron count. Good. All right. So we need to pause there and mention something that was going on in the background. Delete. Just need a little bit more space, so I'm rearranging some things. Dun, dun, dun. That's still not going to be enough space, but whatever. Okay, now we've taken care of the aryl halide. Now we need to deal with the vinyl boronic ester. So let's redraw that vinyl boronic ester. And I want to show you something that's going on in the background with that vinyl boronic ester, something that's actually important for the reaction to happen. Boron has an empty p orbital on it when it's only attached to 3 things. You got to dig way deep and think back to 351 to remember that. And hydroxide, which we have included in the reaction, will actually attack the boron and bind to it to make an electron-rich boron species that looks like this. So 4 things now attached to boron with a negative formal charge on the boron. All right. So that's a side equilibrium that's happening all the time, but you actually have to get to the negatively charged boron species to do what we want to do next. The next step of the reaction is called transmetallation, or you could call it ligand exchange. We don't need to push arrows for the reaction. I'm going to simply illustrate what happens. And we'll try to do that. Shrink. Move a little bit. We're going to see that the boron delivers the carbon and makes a new bond between this carbon of the boronic acid and the palladium. At the same time, the bromine ligand comes off, and at the same time, you're left with boron bonded to 3 hydroxyl groups. Okay, the new complex that's going to be made at this point still has the 2 triphenylphosphine ligands on it, and it's still got the phenyl group on it, but now that vinyl group that used to be attached to the boronic acid is now attached to the palladium. Why do we call that a transmetallation? Because the palladium is one metal, and we're going to pretend like the boron's another metal. Boron's actually close to the sort of metal side of the periodic table. You go down one row of the periodic table, you go from boron to aluminum, which is a metal. So boron's an honorary metal. And so this transmetallation involves transfer of the alkyl group, or this vinyl group on boron, from boron to palladium. We won't worry about the mechanistic details of that reaction, okay? You may just need to accept it as fact. It's a swapping of ligands. We're not going to push arrows through that. Yes?
In the book, it talks about how to prepare the boronic acid. Do we know
Yep.
about that?
We'll mention that in a little bit. Yep. Good. What else? So now you can see where we're going. Look at the product we want to form. The product has this new bond between the benzene ring and the vinyl group. So, and we've got both of those groups on the same metal. So now we're set up for a reductive elimination step. I can't write sideways. Here, let me turn my whole self sideways. You can't turn the paper sideways if you're using an iPad because the screen just rotates itself. It's kind of obnoxious. Okay, we can push arrows if you want through that reaction. Again, choose one to be red and the other to be blue. We make a new carbon-carbon bond. We break a carbon-palladium bond, and electrons go back on the metal. And the product that gets released has the benzene ring here. Here's the new bond that we made. And the metal, importantly, the catalyst is regenerated. I guess I should have added that before that reductive elimination step, notice that the ligand exchange does not change the properties of the metal. We still have two X-type ligands. It's still a D8 metal. It still has 16 total electrons. When we do the reductive elimination, we go back down to palladium 0, D10, 14 electron complex, and we're ready for another turn of the cycle. Okay, so what do you need to be able to know? You need to be able to recognize what an oxidative addition step is, what a reductive elimination step is. All right, let's say just a little bit about preparing for a Suzuki reaction. Aryl halides, you know how to make. That's electrophilic aromatic substitution. You've done that before, so that's not hard. Vinyl boronic esters, that's new, and your text does show you how to make those. So I'm going to give you the options that your text uses for making a boronic acid or a boronic ester. Okay, so one easy strategy, and I guess both of these strategies that are shown from your text are actually boronic esters, so just erase. Sorry. You can start with an aryl halide. You can do the same reaction that we did in generating organolithium reagents. It's called halogen metal exchange. We did this at the very beginning of class when we wanted to generate an organolithium reagent from an alkyl halide. We didn't talk about the mechanism, and we're not going to. Basically, lithium donates electrons to the molecule, which then loses bromine. Once you make that organolithium reagent, making the boronic ester is actually pretty easy. You start with a boron that's bonded to 3 methoxy groups, and you end up with a new carbon-boron bond with only 2 methoxy groups attached. Here is the third. It left from the boron, and then here is the lithium, which is a counter ion. We won't talk about the mechanism, not because it's too hard, because it's actually pretty easy, but just because it's boring and we have other things to talk about. Effectively, electrons from this carbon-lithium bond would attack the empty p orbital on the boron to give you an intermediate that would have a boron that's negatively charged, and then one of the methoxy groups would leave. That's one way to make a boronic ester. The second way, and that's if you want an aryl boronic ester. I'm not sure why I'm choosing to write in red now. That was weird. Boom. Nope, not blue, black. There we go. If you want to make a vinyl boronic ester, this is actually pretty easy too. You can actually use a reaction you learned in 351. So you take an alkyne as a starting material, and you do a hydroboration reaction. The reagent is a boron with a hydrogen on it, and then 2 other OR groups. I'll give you an example of one of these only to prevent you from freaking out about it when you see it. The reason you'd freak out about it is because look at those rings. But you can think of those 2 oxygens as just OR groups. The key functional group is the BH bond. Here's the mechanism of a hydroboration reaction. The carbon-boron bond starts to form first, and then hydride gets delivered to the more substituted carbon where positive charge starts to build up. And you end up with this, again, boronic ester, in this case, a vinyl boronic ester. Okay. Let's do a couple examples of the Suzuki reaction. So let's just say that we want to make the molecule that we sort of started out this chapter with. Suppose you want to make this via a Suzuki reaction. So, which bond in this starting material can you make via the Suzuki reaction? The aryl-aryl bond, right? And in a Suzuki reaction, one side's got to be a halide and the other side's got to be a boronic acid or ester. So we'll use a little red squiggly line to indicate that we're going to make that bond. Choose which side you want to be the halide and which side you want to be the boronic ester. Doesn't actually matter which is which. So we'll choose the right by letting the one on the left be the, I don't know, whatever. Okay, fine. Let's have this be the boronic ester. Keep all the methoxys together. And then what would the other starting material be? And on which carbon would I put what functional group? The halogen on the meta to the cyano? Okay, good. That's really all there is to it, thinking backwards through the Suzuki reaction. Okay. All right, other questions? Okay, yeah.
Just for those earlier reactions, do we just assume that if you replace the OR with just an OH, then that would work for the acids?
For the boronic acids, yes, you can assume if you replace the ORs with OHs, that would be fine. Okay. Anything else? All right. Let's now introduce, and we'll see how far we get on the next Nobel Prize winning reaction, which is called the Heck reaction. So this is going to look really similar. That is legitimately the guy's name, Professor Heck. It's true. All right, so what are the substrates for the Heck reaction? Also, like the Suzuki reaction, for the Heck reaction, you can use an aryl halide, but you could also use a vinyl halide. So this is an example of an aryl halide. An example of a vinyl halide would be something like that, okay? Then the other partner, and this is the actual sort of beautiful thing about the Heck reaction, the other partner is just an alkene. You don't need any particular functional group on the alkene, though it helps if on one side you have something that's electron deficient, okay? Here I'm saying Z is usually like maybe a carbonyl or some other electron withdrawing group, okay? Notice the contrast between the Heck reaction and the Suzuki reaction. In the Suzuki reaction, we also had an aryl halide, but over here on the vinyl group, we would have needed a boronic ester. No need, or boronic acid. No need for that for the Heck reaction. This is actually going to make a bond between the carbon in red and the carbon in blue, and we don't need any particular functional group on this carbon. So that's unique. When you can start with a CH bond and replace it with something else that's useful, that's really good chemistry. So the product of the reaction makes a new bond, and we'll just highlight, I don't know, in orange, the new bond that we make. And of course, there wasn't any stereochemistry to speak of on the alkene side of the equation, right? But the reaction is selective for E or trans stereochemistry of that alkene starting material on the alkene side, okay? There's actually a, I'll just write here that there isn't any stereochemistry to worry about, but if there, for the aryl halide, but if there were for the vinyl halide, the stereochemistry is unchanged. I'll show you an example of that in a little bit. The catalyst that, or the reagents that do this reaction are palladium, this time palladium diacetate. OAC is an abbreviation for the conjugate base of carboxylic acid. So if this overall complex is neutral, what is the oxidation state on that palladium? +2, okay? So unlike the Suzuki reaction, the reagent you use for the Heck reaction is actually palladium-2. You also need ligands. Sometimes people will synthesize complexes of palladium with ligands already there. Other times you don't need to. You just put in the source of palladium and you add the ligands and the complex assembles itself in solution. So there's ligands that are involved in this reaction. They are phosphine ligands, but their structure is weird. So let me just show you the structure. It's hard to draw. It involves phosphines. In this case, it's like triphenylphosphine, only instead of benzene rings, they're all toluene rings. And you see I'm rapidly sort of running out of space. It's found that the structure and the properties of the ligands can really dramatically influence the reactivity of the catalyst, the palladium metal. So you could ask why they chose to use this particular phosphine ligand instead of triphenylphosphine. The answer is, I don't actually know, but probably they tried both and this one worked better. There's sometimes people screen various ligands to see if you change the identity of the groups on the phosphorus, does it change how the reaction goes? There are people such as Professor Matt Sigmund at the University of Utah who are trying to analyze all the data and understand the basic principles that govern which phosphine ligands are going to be best. So a lot of people working on this. We're not going to investigate that in any level of detail. We're just going to call that PR3 for a phosphine ligand. Your text will use something O-tolulyl and put it in 3 around the phosphine. That's an ortho-toluene ligand on a benzene ring is what you're getting at there. Okay, so how will you recognize the Heck reaction? First, it's palladium-2. Second, it's going to use a slightly different phosphine ligand, at least in your text, than was used for the Suzuki reaction. We don't have time today to do the catalytic cycle for the Heck reaction. Instead, what I'd like to do is just show you a few different molecules that work in the Heck reaction so you can get good at predicting products. So here is a vinyl halide. Notice that the stereochemistry of this double bond is E. And we'll couple it with this vinyl, with this alkene, this olefin or this alkene, in which we have a terminal alkene with a cyanide group. We'll use the same conditions I've written above, so I'm not going to repeat them here. I'll just call them Heck conditions. Here is the carbon on the alkene that we'll form a new bond with. Here is the carbon on the vinyl halide that we'll form a new bond with. I'll show you the product. Notice that on the vinyl halide side, I'm going to illustrate in orange the new bond that we formed. Notice the stereochemistry there doesn't change at all. In other words, on the vinyl halide side, this double bond is still E. On the other side, where we make the alkene, we're going to selectively make the new bond on the trans side of that alkene. So this one stays the same, and the reaction is selective for E stereochemistry on the other side. You can tell that this is the case because if you change the stereochemistry of the vinyl halide but use the same alkene, you see the stereochemistry of the vinyl halide is preserved in the new double bond. So it was Z here, it's or preserved in the same double bond on the other side. So it's Z here, it's Z after the reaction. And of course, the double bond on the alkene side selectively is E. Okay, so on the vinyl halide side, stereochemistry stays the same. On the alkene side, there wasn't any stereochemistry to begin with, but it's selective for E. Okay, we have some more to say about those reactions and some syntheses you can do after that point. So get going on that and stay tuned for our last time together on Wednesday. I will see you then.